Okay, we have a YouTube, as you see, with a different sections. We have section A1 for the left one, A1 equals to 10 centimeter square and A2 equals to 5 centimeter square. Initially, we have mercury. Okay, so as we have a P0 applied by the external atmospheric pressure, P0 here, and we have P0 at the right side. So we have the same level on the right side and the left side of the YouTube. This is the initial state. Okay, we poured a quantity of water on the right side. Okay, we have 100 grams of water are then poured into the right arm as in figure B. So here we put a quantity of 100 grams of water. We can say M of water added equals to 100 grams. Okay, as you know, we put this quantity of water at the right side. In this case, the left side will rise to a height h. So here, this side fall down, and this side get up a height h. Okay, we can say here we have a height h1. Okay, h1. Okay, first of all, part A, determine the length of the water column. In the right arm, I want to find the length of the water column, the total length. I want to find the total length of water. We can say here we have H water. I want to find it. Okay, it's easy. You know we have a cylindrical shape of the side. We have the mass. We can say the volume of this quantity equals to the section A2. Okay, part A equals to the section A2 times the height. We can say the height h omega. I want to find h. The volume, I don't have the volume, but I have the mass. You know, the density of water equals to mass per volume. So we can say volume of water equals to the mass per density. Okay, so here we can say equals to m water divided by the density of the water, which is equal to 1000 kilogram per meter cube, or 1 gram per centimeter cube. So now I want to calculate H water equals to M water divided by A2 times rho water. We get M water equals to 100 gram times 10 power minus 3 to have the unit in kilogram divided by A2 equals to 5. We can put it in anyway, we can put the unit in a gram and centimeter to have finally the height in centimeter. Okay, if you want, we can put it like this. You know, the mass of water equals to 100 gram divided by A2 equals to 5 centimeter square times the density of water equals to 1 gram per centimeter cube. Okay, so we calculate the height of water we get will be 20 centimeter. So we have 20 centimeter of water in the right side of YouTube. Okay, this is part A. So we have H water equals to 20 centimeter. Part B, given that the density of mercury equals to 13.6 gram per centimeter cube, what distance h does the mercury rise in the left side? I have to find small h, this value. You know, here we have a hydrostatic fluid. We can apply same level, same water we have, same pressure. Okay. First of all, as we have a static state, we have a static fluid, we can choose the interface between the water and mercury. We can take a point A. Okay. And at the same level, we can draw point B. Okay, we have the same level, a point B. Anytime you have a hydrostatic fluid, you can choose 2 points. If you have YouTube or if you have any kind of this configuration, you have to take 2 points to compare PA and PB, and for each point you can take another point. Like in this case, we can take PA equals to PB, and you know PA between the point A and the point A prime, we can apply the famous hydrostatic relation, P low equals to P above plus rho GH. Okay, so now I want to calculate small h. I repeat, as we have a hydrostatic state, we take 2 points. Always you have to take the point at the interface between fluid 1 and fluid 2, between water and mercury. You know, PA equals to PB. Okay, PA equals to PB. We have same level, same liquid, because A, it can be in the mercury and it can be in the water. Okay, it's between. Okay, we can calculate first of all PA, and after we calculate PB. PA, we take A and A prime. You know, between A and A prime, we can apply PA equals to PA prime plus, between A and A prime, we have water. So we can say rho of water times G. Between A and A prime, we have H water already calculated equals to 20 centimeter. So from this relation we can calculate PA. Okay, we can use it in the other side. So PA equals to PA prime. You know, A prime is a point which is connected with the as a point A prime we have P0. Okay, we have P0 because A prime is in contact with the external atmospheric pressure. So PA prime equals to P0 plus rho of water equals to 1000 kilogram per meter cube times 10, or we can say 9.8 times H of water equals to 20 times 10 minus 3. Don't forget to convert centimeter to meter. Okay, you know PO equals to 10.5 Pascal. We get here PA, which is equal to, here you can keep this relation and we can use it later. We can say here just PA equals to PO plus rho water GH water. Okay, we can use like this. PA. PB. PB. Okay, here for PB we have between, we can take between B and B prime. Okay, so between B and B prime we have PB equals to PB prime plus rho. Between B and B prime we have mercury, so we have rho of mercury times G times the distance between B and B prime equals to H plus H1. Okay, we have H1. You know, here we have H1, the same H1 here and here. We have the same level. So we can say here directly the distance between B and B prime equals to H1 plus H. So we can say here H plus H1. So we can write, you know, B prime equals to P0 because it's equal to P0. We have only P0 applied at this point. So we can write PB equals to P0 plus rho Hg G H plus H1. So we have equation 1 and we have equation 2. You know, PA, if I write PA equals to PB, we can say PA equals to PB. Let me clean this one. Okay. And this one. We have this equation and this equation, PA and PB. So we can say here PA equals to PB. So we can write here PA equals to P0 plus rho water G H water, okay, equals to P0 plus rho Hg times H plus H1. Okay, we can eliminate P0 and P0. As you see, a row of water is given, G is given, is known, H water equals to 20 centimeter, a row of mercury equals to 13.6, G, I want to calculate H, but I don't have the value of H1. So to calculate H, we have to find H1. Here, so to find H1, you come here. Initially, we have the mercury at the same level. When we put a quantity of water here, we have a certain volume of water comes down and the same volume comes up. Okay, so we have the same quantity of volume. As we have a different sections, we can have a different height, but we have the same volume. If A1 equals to A2, we get the same H down and H up. We get the same value, the same height. But in all the cases, we have the same volume. So the volume here equals to the volume here. Okay, we can say V1 and V2. So we have V1 equals to V2. Okay, you know V1 here we have H1, V1 equals to the section A2 times H1. We have A2 times H1, okay, equals to V2 equals to the section A1 times H. Okay, so we can put H1 in function of H to eliminate the two unknowns. So here we can write H1 equals to A1 divided by A2 times H. So we come to the equation 3. We can write equation 3. We have here row water G H water equals to row mercury G H, I need to calculate it, plus H1 equals to A1 divided by A2 times H. So we can write here H equals to a row of water equals to 1000 kilogram per meter cube, G equals to 9.8, H water equals to 0.2 meter divided by H mercury equals to 13, okay, times 13.6 times 10 power 3 to have in kilogram per meter cube times 9.8. Okay, here we have 1 plus A1, we have 10 divided by 5. Okay, we can calculate the value of H. It will be 0.490 meter. This is the height of the mercury up the initial level. Okay.